Hi, I'm Dr. Oscar Wong, and thank you for tuning in to the third video in our Research Primer series by Research Lab X. So in this video, we'll cover advanced technique in biostatistics, include multivariate regression and propensity score matching. So I strongly recommend everyone to watch our previous video before diving into this one. So we'll be describing how we use these methods and some limitation that we have to keep in mind while using these techniques. So I hope you're ready for this exciting episode, where we explore some advanced technique in analyzing data. So in the previous video, we have covered some basic statistical tests that we can use for hypothesis testing. However, in the real world, there are several limitations to conducting research based on observational data, such as cohort studies. So importantly, observational data does not account for confounding factor. Let's look at the example study where investigators want to see if red meat consumption affects the risk of colorectal cancer. So confounding factor could include smoking, BMI, sex, and many others. Although we could try to select only patients with similar BMI, sex, or age, this would still have some problem. First, if we selected only patients with similar smoking habits or BMI, then the result of our analysis will only be applicable to this subtype of patient. Hence, it will be of little interest as it cannot be generalized. Secondly, selecting only similar patients will limit the number of patients we can include in our analysis, which can result in quite a small sample size. So this would reduce the statistical power of the study, which is undesirable. So how do we solve that problem? So the solution to this problem regarding confounding in observational data is actually what we call multivariate regression models. You might have seen it in other medical literature published before. So this allows us to estimate the effect of many predictor variables or independent variables on the outcome of interest. So using the previous example, we can use a multivariate logistic regression to estimate the effects of a high red meat diet, smoking, age, and BMI on the odds of colorectal cancer. So if you use any statistical software to conduct multivariate regression, the result will look something like what we are showing on the screen. So let's interpret the result of the analysis. First of all, let's take a look at the basic formula of multivariate regression. So Y is the outcome of interest, and in the previous example, it will be the risk of colorectal cancer. Next, we have beta 0. This is the y-intercept, which is a constant term specific to each model. So this is usually presented in the first line of the result, output as highlighted in orange. Next, we have the predictor variable, which are represented by x1, x2, and so on. In the previous example, the predictor variable will be BMI, consumption of red meat heavy diet, smoking habits, age, gender, and so on. So this will be listed sequentially in the output section of the statistical software that you are using. Each of the predicted variable will have its own corresponding beta coefficient, which is highlighted in blue. So the meaning of each beta coefficient depends on the multivariate regression model we use. So don't worry, we'll be describing this in greater detail in the next slide. Okay, so as you can see on the slide, we're showing the three most common multivariate regression model available, and the choice of which depends on the outcome of interest. So first of all, let's look at the first one, linear regression. So this is used when the outcome of interest is a continuous variable, and this will be used if you wanted to investigate the factor associated, for example, with blood pressure. In this case, the beta coefficient of the predictor variables means how much the outcome of interest increases per unit increase in the predictor. For example, how much blood pressure increases per unit increase in BMI. Okay, so the next one we have logistic regression, which is used when the outcome of interest is a binary variable. So this is relevant to the example where we've been using of investigating risk factor for colorectal cancer. So the beta coefficient is the natural log in the odds of the outcome increases per unit increase in predictor. So the reason why it is the natural log of the odds instead of the raw odds is because logistic regression uses a logic link function. So finally, we have Cox regression analysis, which is the standard for time to event analysis. A very common utilization of the Cox regression model is for survival analysis. For example, we could be analyzing the risk factor associated with cancer-related death, in which case we can conduct a multivariate Cox regression analysis. Somewhat similar to logistic regression, the meaning of the beta coefficient in Cox regression is how much the natural log of the event rate of the outcome of interest increase per unit increase in the predictor. So due to the limitation in time and to provide a more personalized experience for everyone, we'll be delving deeper into how to conduct the different multivariate regression model in the commonly used software such as R or Stata in the Research Lab X cohort study packages. Okay, that being said, so let us try to go through some of the key steps in conducting multivariate regression analysis. First, you have to build the model by choosing which predictor variables are important to include. There are several techniques available to choose the predicted variables. First, we can rely on expert opinion. Of course, this is important as we should include predictor variables in the analysis because they could theoretically have impact on the outcome of interest rather than to assume a small p-value. So for example, we all know that high red meat diet can cause increased risk in colorectal cancer. Or we can also include things like smoking habits or gender in the model because previous literature have demonstrated that they are significant predictor factors for colorectal cancer occurrence. Alternatively, we can use statistical techniques such as stepwise regression or least absolute shrinkage and selection operator, also known as lasso regression. So these are commonly employed techniques, and the purpose of implementing these techniques is to select for only significant predictor variables in the final multivariate model. This is to prevent model overfitting for including too many insignificant predicting variable, which should result in the final model not being generalizable. This is because if you include too many variables, it can cause the model to predict outcomes in the training set very well, but at the cost of struggling to predict outcome with the data outside of the training set. So once we're done with selecting predicted variables, we are ready to conduct the analysis. So once you click and conduct the analysis, there are several tests that we should look at and their value to estimate the adequacy of the model. Some important values to take note are F-tests, which tests whether the regression model provides a better fit to a dataset than a model with no predictor variables. You can take note of the F value as well as the corresponding P value as a measure of model adequacy. Additionally, you can take a look at the R square of the model, which measures how much the predictor variable can explain variation in the outcome of interest. You can also look at the mean square error, and a lower mean square error generally means a more accurate model. Finally, you could also observe the beta coefficients of each predictor variable and the p-value for the test, which allow you to interpret which variables are statistically significant in the model. Finally, after selecting the variable and running the analysis, we can proceed with validating the model to ensure it is an accurate predictor of the outcome of interest. This is to identify any overfitting that could occur, as a model that too closely fits the training data might not be generalizable to external data. So first of all, we can do a quick inspection of the beta coefficient, checking if it's in line with published literature. This involves checking the magnitude and the direction of the variable. For instance, in the case of colorectal cancer, we could expect smoking to be associated with a large and positive beta coefficient. However, if smoking happens to be associated with reduced cancer risk, then there could be a problem in our model or the data that we have to further investigate. Furthermore, we should examine the predicted range of outcome of the interest to check if that is theoretically possible. After we have examined these values, we can apply the model to other datasets to externally validate it. And one way to do it is to split the dataset you have into training and validation sets. This is possible when you have a large number of patients involved, or alternatively, you can always use external validation cohorts to check the model, looking at the R-square values and the mean square values in those training sets. So like all statistical tests, multivariable regression is not without limitation, so that we are mindful about it when conducting such analysis. Firstly, there could be residual confounding arising from limitations in the data. The data might not have sufficiently granularity to investigate the effects of a predictive variable on the outcome of interest. For example, for red meat consumption, how can we quantify the amount of red meat a person normally eats per meal? If we do not stratify meat consumption with enough strata, we might not be able to accurately estimate the effect of the predictor on the outcome of interest. Next, we could encounter the problem of multicollinearity, which happens when two or more predictor variables have a strong linear trend. In an ideal multivariate model, the predictor variable should be strongly associated with the outcome of interest, but weakly associated with each other. However, this is not the case if multicollinearity is present, which could cause inaccurate estimation of the beta coefficient, and also probably overfitting the data as redundant predictors have been included. So, how do we solve the problem? To prevent the problem, we can create a correlation matrix which plots linear trends between all the variables. We can then look for possible collinearity in predictor variables that are strongly associated and remove redundant variables. Alternatively, we can use more objective measures alongside the correlation matrix, including the variance inflation factor or VIF. In most cases, a VIF higher than 10 indicates possible multicollinearity in the model. We can then look at the correlation matrix to see which variable has a strong linear trend and remove the necessary variable for a more accurate model. Okay, so coming back to limitation of multivariable regression. A multivariate regression model also assumes a linear relationship between the predictor and the outcome. However, we should not always assume that this holds true. In order to test for this, we should also plot several scattered plots between the independent variables and the outcome of interest to check for linearity. If there's no linear relation, then we can conduct a transformation of the independent variable via exponential, natural log, or other function, so that it more accurately models the outcome of interest. Finally, a limited number of predictors can be included in the model to prevent overfitting of the data. As a general rule, we should include only one predictor per 10 patients in the data set. Hence, if there is a limited amount of data, it will be difficult to fully account for all variables. As such, we should rely on expert opinion and theoretical knowledge to select the most relevant variable that will potentially have the largest effect on the outcome of interest. Okay, so I hope those information were not too overwhelming and helpful. So other than multivariate analysis, another commonly used technique to address confounding factor is what we call propensity score. An example shown here is a study which is showing a propensity score analysis of a patients undergoing surgery alone versus surgery combined with neoadjuvant or adjuvant chemotherapy for gallbladder cancers. However, what are propensity score and how are they used? I'm pretty sure you're quite confused about it. Don't worry, we'll be discussing it in greater detail in the next few slides. So, propensity score are especially helpful when comparing interventions in observational study. For example, in the article shown in the previous slide. This is because the use of propensity score matching helps to achieve balance in observed covariates, and it reduces the influence of confounding factor on the outcome of interest. But one thing that we should note is that propensity score matching is not a replacement to a randomized control trial, because the randomization process achieves balance in both observed and unobserved covariates, while propensity score matching only balances the observed characteristics. Okay, so as the name suggests, propensity score, we'll be calculating a score and then we further match patients into different cohorts. So the first step in propensity score analysis is deciding the covariates used in the analysis. Comparing to multivariate analysis, there's no limit on the number of independent variables used to calculate the propensity score. This is because there's no risk of overfitting the data, And in fact, the aim of propensity score matching is to balance the two groups as closely as possible. So the more variable included, actually it's the better. So additionally, there's no need to assess for linearity between the predictor and the outcome. So this theoretically makes propensity score less tedious than multivariate analysis, where you have to account for multicollinearity or a linear relation between predictors and outcome. However, there is a need to clean the data before calculating propensity score. It's because patient cannot be missing data for any of the included covariates. For example, if one of the patient is missing data for one column like age, then the standard practice is to fill in that value with the mean of the remaining values. So this is to ensure that all data points are included to increase the statistical power of the analysis. So once you clean the data and you decided on the covariates, we can proceed to calculate propensity score and conduct analysis. So once we calculate the propensity score, there are two methods that we can use to account for confounding. First, we have propensity score stratification. That's when patients with similar propensity score are grouped into strata and outcomes are compared within the strata. The benefit of this method is that all data points are included in the analysis, hence greater statistical power. But furthermore, by analyzing outcome over different groups, we could possibly find interesting trends in specific strata. For example, certain intervention would benefit patient with high propensity score, but not in patient with low propensity score. But however, there are still some drawback to this method. First of all, there could be some variability within each strata with a range of propensity score included, which result in residual confounding. Furthermore, this method doesn't provide granularity in the data, specifically for the underlying predictors. Another common method of using propensity score is propensity score matching. This is where patients from different treatment groups are matched together by propensity score. There are many different ways to match patients, and some commonly used methods are exact matching, optimal pair of matching, Cosinor exact matching, and many others. It is also possible to specify the matching ratio, where you can match one control patient to one treatment patient, or two control patients to one treatment patients, etc. While there is still ongoing debate in the statistical community about which matching method to use, the choice of the method and ratio should be specific to your dataset. Ultimately, the aim of matching is to achieve the best balance between including as many patients as possible, while also ensuring that the propensity score are as similar to each other as possible. Because this allows for maximum statistical power and also to adjust for confounding factor as much as possible. So once we do propensity score matching, it's also very important to assess for balance. And this can be done via inspection of a love plot, and the sample can be seen on the slide. The white color dots refer to the standardized mean difference prior to matching, while the black dots are the standardized mean differences after matching. As you can see, there's a great reduction in standardized mean difference after propensity score matching, indicating that a better balance has been achieved. So let us first delve into how standardized mean differences are calculated to better appreciate how propensity score matching increases balance in the observed covariates. So the standardized mean difference (SMD) is calculated as the mean differences divided by the standard deviation of that variable. For example, the differences in body mass index between groups is 3.0, and the standardized deviation is 4.0. So the SMD would be 0.75. Conventionally, SMD less than 0.1 or 10% is considered to be well balanced between groups. So let's go back to the previous graph, and we can see that on the love plot, we can see that the propensity score are well matched as all covariates have a SMD of less than 0.1. So now we have a better understanding of propensity score. Let us see when it is appropriate to use this technique. Firstly, propensity score analysis is useful when there's imbalance in treatment groups. This can be a result of differing indications in clinical practice, for example, when one treatment is preferred in older or sicker patients. Propensity score are also preferred in situations where there are a smaller number of data points but a large number of independent variables. With multivariate regression, it is standard practice for there to be one predictor per 10 observation. Hence, in these cases, it might not be possible to account for all independent variables via regression, but do remember that propensity score analysis has no such limitation. So, even though propensity score analysis sounds really good, really convenient, there are still things that we should look out for. Always be mindful when reading articles using such technique. Statistical techniques such as propensity score analysis needs to be conducted with care and should not be a replacement for randomized trials as previously mentioned. Furthermore, we should always look out for these points to ensure that the propensity score analysis is well done when reading and conducting research. Like what we have mentioned before, we should read the methods to determine how the independent variable were chosen and how it was calculated. Importantly, we should always look for how balanced the data is after matching by looking for the love plots and checking the SMD, standardized mean differences. So just to summarize, in this video and the previous video, we have run through most of the statistical knowledge required to conduct a well-designed study. We presented a clear picture of what p-values and confidence interval mean, as well as steps to hypothesis testing. Additionally, we have described the different types of data and for the different statistical tests depending on the type and distribution of the data. And in this series, we talk about techniques that you can use to account for confounding factors, including multivariate analysis and propensity score matching. So I really hope that was helpful and it can help you to navigate in literature or when you want to design your own study. Thank you again for listening, and stay tuned for our next episode, which is Fundamentals of Systematic Review and Meta-Analysis. Thank you very much for tuning in. Hope you enjoyed the episode today, and Research Lab is here to help you to find the answers you need. We have a unique approach to research that emphasizes collaboration, creativity, and innovation. Our team is available to provide guidance and feedback throughout the process. If you are interested in learning more, contact us at Research Labs today using the link shown. Thank you.